explain that big picture in terms of where we're going in the future. So today we've asked him to challenge our thinking in relation to how the remote sensing community and the GIS community can work more closely together. So would you please join me in welcoming Mike?
Thank you very much, Peter, for that introduction. Thank you for the invitation to be here. This is going to be something rather different. I see myself not as a remote sensor, but as somebody at the end of the extreme end of the supply chain of remote sensing that makes use of remote sensing in integration with many other sources of information. And what I'd like to do today is to present you with, in a sense, an update on the status of that area and where it might be headed. So just a very brief outline. I want to talk about various ways in which the geospatial world is expanding. And I'm sure you've noticed already, if you've used your smartphone recently, that a tremendous amount of geospatial information and geospatial services are now available through that medium and through other media. I want to talk then about the way in which the average citizen is getting engaged with the geospatial world and, remarkably, with remote sensing. And also the concept of neogeography, which really captures, I think, many of these departures. That will lead me briefly into mention of big data, which is, if you've been reading the media recently, a very hot topic. Then I want to talk about crowdsourcing in the specific area of validation of remote sensing and synthesis, which I think is quite an exciting area. I want to talk a little bit about ground-based remote sensing because it's another major source of information for the kinds of things I do. And then I want to talk briefly about future prospects. So this will be a very quick, unfortunately, overview of what to me is a very exciting and elaborate field. So let's start here with the world's perhaps most conspicuous example of citizen engagement in the geospatial world. This is a project called OpenStreetMap. It was begun in 2004 by a student at University College London, Steve Coast, and it spread rapidly all around the world. And its basic idea was to produce a crowdsourced map, a volunteered map of the world that would be accessible to everyone in digital form. Here is early coverage of central London. Imagine people on bicycles, people walking the streets of London, writing down street names, capturing their tracks in GPS, and then integrating all of that into a single worldwide map. And perhaps the most spectacular application of OpenStreetMap came in January 2010 after the Haitian earthquake, when all over the world, within hours of that earthquake, volunteers in their hundreds, in fact thousands, got together to create a map of Haiti. Far better than anything available to that point and far more relevant to the rescue effort. This is the coverage of central Port-au-Prince as it existed just a few hours after the earthquake, assembled by people around the world. If you could see the details, you would notice that many of the streets have no names. And that, of course, tells a story about how this was done. It was done by relying on imagery, fine resolution imagery distributed by companies like Google, Digital Globe, and used to create essentially a map. No name results, of course, because the street names are not visible from space. But nevertheless, many of the street names were available. They were supplied typically by expatriate Haitians located in different parts of the world that could be accessed by volunteers. The important point, though, is that virtually all of this information was assembled remotely and relying heavily on remote sensing. The success was immediate. This was officially accepted as the base map for the UN relief effort, and most remarkably, I think, by the US military as a volunteer, a crowdsourced map alternative to the traditional production mechanisms. This is, as I said, perhaps the most spectacular example, but nowadays it is one of many, many examples of the use of volunteer effort to create geospatial information, raising many very interesting questions, I think. One question being, if the average citizen has the ability to make a map of anything, what would the average citizen choose to make a map of? And the answer, I think, is quite remarkable. It is essentially something very different from what has traditionally been mapped. Many of these examples really open the box on what we can do with geospatial information. Here's one issue that arises here. This is a map of the UC Santa Barbara campus. This is as it appeared in Google Earth some years ago. And superimposed on it is a fine resolution aerial image, which I have very carefully georegistered. And notice the offset. Right? So my image is offset approximately 15 meters to the west of the Google Earth image. This is almost entirely the result of misregistration in the Google Earth image. You may notice also that the street names, which are distributed by Google, in fact don't match the Google Earth image because they are much more accurately positioned, and they do agree very well with my image. So what do we learn from this? We learn that people who rely on imagery, particularly imagery in Google Earth, inherit the misregistration. And when Google replaces that image, as it did shortly after this, with a much more accurately registered image, those misregistrations are inherited. So you can refer to this, if you like, as the Google datum, noting that every so often when Google replaces its imagery, the Google datum shifts. Here's an example of my own department failing to recognize this. This is a press release from the department dated 2007, and it gives the location of the department resolved to 100th of an arc second, which is approximately 30 centimeters. I was initially very excited about this because I saw it as a mechanism for finding out who actually controlled the department. All I needed to do was find out whose office that location was in. It turns out, unfortunately, of course, that it inherits the inaccuracies in the Google datum, 15 meters off. But worse than that, whoever transcribed this into the press release got one of the more significant digits wrong. So that location actually turns out to be in a park several kilometers from the department. So this is a welcome to the world of neogeography. And there are two aspects to the definition of neogeography. The first is a redefinition of the role of expert. Because we have here citizens, largely untrained amateurs, working in their own time, producing geographic information which is in many respects as good as what we have traditionally had. And that's, I think, a very exciting and very significant departure. The second aspect is that the perspective is extremely user-centric. So this is the world of the user-centered maps that you get on your iPhone, useful only for one user, the user located at the center of the map. Transitory maps, valid only at this moment. 3D maps, giving the view from the street, and all of them displayed on the user's device. A very, very different world from the traditional world of geospatial information. So how is this impacted by satellite-based remote sensing? And how does it impact, in turn, satellite-based remote sensing? And as I said at the outset, I see myself, and I see all of this domain, as very much at the end of the supply chain of remote sensing, where I think the scientific objectivity of remote sensing meets the messiness of human society. And in remote sensing, we spend, of course, most of our time in that wonderful world of scientific objectivity. These are examples where, inevitably, that meets human society in its messiness. Let me give you just three examples, and I think all of these three speak to how remote sensing is being applied in this world of neogeography. So here's the first. This is the work of Peng Gong at Tsinghua University. He's also at UC Berkeley, and his colleagues. This is recent work in which they've done a meta-analysis of all the papers published on land cover mapping using remote sensing. And those dots on the map are simply the central points of several thousand papers describing various land cover mapping projects. Interesting, though, as you look at that map, to note that it's not essentially a map of biodiversity, critical hotspots on the Earth's surface. It's not a map of the difficulty of mapping land cover. Instead, it's largely a map of wealth. The countries which are most mapped for land cover typically are the most wealthy countries. And down in the bottom left-hand corner, there's a scatter plot, which is a log-log scatter plot of the number of mapping projects versus the GDP of that country. And you can see there's a very simple linear relationship. So here then is the world of land cover mapping meeting the messy world of human society. Here's another example. This one is from Google Maps. And this is what you would get if you went to Google Maps and asked for a map of the Himalayan region. You did it from, let's say, this room. And you will notice that there are two kinds of dashed lines on this map. The internal boundaries of China and India are dashed, but also various boundaries in the Himalayan region are dashed because they are uncertain. They are politically in dispute. So if instead you were to make the same request from a machine located in India with an IP address assigned to India, this is what you would get. You would get a different map. You would get a map according to the official policy of India, which is that Kashmir belongs to India, Arunachal Pradesh belongs to India, there's no doubt about those boundaries. And if you were to do the same thing from China, not including Hong Kong and Macau, this is what you would get, the official Chinese policy. So the message here is that in this messy world of humans, maps are not. There is not simply one map for all. There is the map according to different perspectives, different national perspectives in this case, but we can extend this example in many, many different directions. And then finally, the third example comes from Google, Microsoft, and Yahoo, who in June 2011 made an agreement to adopt a common markup vocabulary, which they called schema.org, which could be used for anyone around the world to give meaning to their maps. And essentially what it is a common classification system for geographic features. It's called schema.org, you can go to it, and here's a small part of it. Everything at the top of schema.org is a thing, and then anything which is georeferenced under that is a place. And here are different categories of places in the category sports activity location. And what you will notice here, of course, is that this is the view from Mountain View, California. This would make very little sense to someone located in any other parts of the world. It will particularly make very little sense to an indigenous population, an indigenous group in Australia, or many other parts of the world. This is actually a very interesting echo of something that occurred about 100 years ago, which was a project called the International Map of the World, which was a project to create a single 1 to 1 million map covering the entire Earth. And there was a single classification system, a single form of cartographic notation. The millionth map eventually covered large parts of the Earth, but notice the similarity to the map I showed earlier of land cover mapping. This again is a map covering much of Europe, North America, and parts of Africa, and probably one of the factors guiding the coverage of Africa was colonial domination of Africa. So I believe we are very much at a fork in the road in this world, and it's a fork in the road between a global approach, a belief in one global map, one markup language, one universal consensus on what to map, originally promoted in London in 1913, and then, oddly, almost 100 years later, in California, in Mountain View, California, in 2011. That's one extreme. The alternative is to recognize that there are many maps, many communities, many cultural, linguistic variations on what to map, to give mapping a basis in community, which is, I think, very consistent with the ideals of a new world native geography. This is, as I say, a very important, I think, fork in the road which we currently face in this field. Should we move globally into uniformity, or should we move locally into a greater sensitivity to language, culture, and other variations? Just to move forward a little bit, one of the, I think, most successful ways in which the community can be involved in geospatial information is in the area of synthesis and integration. So think for a moment about how remote sensing information gets integrated with other kinds of information and is used to produce something of value. This relates to a fire which occurred, a wildfire which occurred in Santa Barbara a couple of years ago called the Hezazita Fire. And at the outset of the fire, one of my graduate students and two of his friends decided to devote the time of the fire, which ended up being about 48 hours in terms of the emergency, devoting that time to building a synthesized map of the current state of the fire. They built this on top of Google Maps, So you can see the Google Maps background. And they synthesized everything that was appearing in Twitter, Flickr, the official information coming from Sacramento, every source of information they could find, synthesized into a real-time map of the fire. Now, think of yourself as a resident of Santa Barbara, owning one of the houses near the edge of the fire, and contrast two sources of information. One is this, unreliable, crowdsourced, synthesized, who knows what the quality is, but current, because it's produced by a dense network of observers who are tweeting and flickering, and therefore is close to real time. Compare that to the official source, which is IncyWeb. It's a source which typically in an emergency like this runs 3-4 hours behind reality. Which would you rather have? Uncertain information now, or reliable information in 3 hours? The fire's at the end of your street, the choice is obvious. The consequences of a positive error, in other words, a rumor that the fire is present where it is not, are much less than the consequences of a negative error, information that the fire is not somewhere where it actually is. So we found over the course of the fire, there were some 600,000 hits on this map during the fire, that people gave much more credence to this kind of information, synthesized from the crowd, than they would to the official information. This leads me then to the world of big data, and the characteristics of big data, which are often presented this way, the 3 V's. Big data is characterized by volume. That's not a problem. We've had huge volumes of information in this world for years. Landsat 1 gave us vast amounts of information. Variety, because we have multiple sources. And velocity, speed. And one of the key aspects of the geospatial world is that potentially we have 7 billion observers distributed densely across the world, each of whom is intelligent and capable of reporting what they see, touch, feel, etc. There is no sampling scheme. Samples are often self-identified in this world. There is no generalizability, therefore, from a sample to a population. There is no metadata to speak of. There is no quality control. Though, notably, I think one has to recognize that quality can be excellent. The quality of OpenStreetMap typically is better than the best official sources. More up-to-date, I think, is one of the key aspects, and in the right context, useful. This is the developing world of big data. And I think a very exciting world with enormous potential. Here's another aspect of synthesis. This is a project called GeoWiki. Many of you, I'm sure, will be familiar with it. It's a project out of Austria, which promotes the idea that land cover mapping can be its validity can be crowdsourced. If you sign up for it, you are allocated a part of the world and asked to compare the land cover mapping with fine resolution imagery and to make judgments about the validity of the mapping effort. Crowdsourcing, therefore, the process of validation. We're increasingly used to the notion of sensor networks, so shifting now from humans as sensors, citizens as sensors, to devices as sensors. Here, for example, is something that I'm sure exists in many parts of the world. This is sensed traffic density on the freeway network of Los Angeles, available on the web, generally done through loop detectors in the highways and video such as you see here. And this, which I find a very compelling example, this is a system built by ESRI and Loma Linda University to manage, create a situation awareness of an emergency in Southern California. Again, this is a fire emergency, and on this map is real-time information, real-time icons representing real-time information about the locations of rescue assets, the state of the freeway network, the locations of hospitals and the state of their emergency room, etc., etc. And essentially, this is what's happening. Real-time information from numerous sources is being integrated, synthesized, and then made available to users. Some of this is remotely sensed, some of it relies on humans, some of it relies on citizens as sensors. And here is perhaps a more familiar kind of example. This is a dense network of sensors in the interests of ocean science, and many, many projects of this nature exist where you have multiple sensors distributed within an environment, capturing information of value to science. So just to try to pull this together, where are we in terms of future prospects? My main point is that the consumer is becoming engaged. The consumer is becoming engaged in the geospatial world, expanding the geospatial world and redefining it. We are now at the point, I think, and I'd cite the example of recent agreements between Esri and Digital Globe, which I'm sure you can find out more about in this meeting, basically bringing remote sensing down to the consumer level, to the citizen level. We've reached the point where access can be fast enough, affordable enough, and accessible enough that we can basically build a consumer economy of remote sensing. I think that's a very exciting possibility. Of course, it depends primarily on the use of remote sensing for simply providing a picture. But we will, I think, move quickly into more exotic examples of remote sensing. So remote sensing then is the basis for numerous applications, georeferencing first, but in future, I think, substantially different. And new kinds of data. And I've talked about networks of ground-based sensors. I think LiDAR has enormous potential at this point, and perhaps exists at a point similar to remote sensing maybe 20 years ago. LiDAR still requiring massive computing resources, still very difficult to access, still expensive. Perhaps at some point in the future, we will reach a community-based system for distribution and use of LiDAR. And then finally, and in my world, one of the most exciting things that's happening is moving into the indoor environment. In the past, GIS, remote sensing, have been seen primarily as outdoor technologies. And the average American, I don't imagine the statistic for Australia will be similar, the average American spends only 13% of their time outdoors, 87% of their time indoors. Our technologies largely are oriented towards outdoors. Large, very exciting and very expensive developments at the moment in the indoor environment, in building mapping of the indoor environment, navigation systems which help people move indoors in complex environments like shopping centers, three-dimensional environments like mines. That world, I think, is still very much in the future. So thank you very much for your attention.